Hi all, this is 5.2, characteristic equation. All right, so we're going to go through a lot of procedures on how to find the eigenvalues and then a lot of properties regarding between eigenvalues and the determinants. All right, so actually before we get into the actual stuff, I just want to take some time and talk about the first paragraph that is in our notes. Okay, so we have some matrix A, right? So matrix A is n by n, right? And then we perform two of the three elementary row operation, which is row replacement and row interchange. Okay, we're just using two out of the three elementary row operation. And the reason of this being, if you remember from a few sections ago, row replacement does not change the determinant. Okay, and row interchange just makes the determinant opposite. Okay, and of course the last one, scaling, which when you multiply any row by a number, that actually scales the determinant as well. But in this case, we don't want to do that. Okay? So we are just doing two of the three, the row replacement, which has no change in determinant, and the row interchange, which just changed the determinant into the opposite sign. Okay, and then let's say through a series of elementary row operation, we get this matrix U. Okay, so our goal is to find out what the relationship we have between the determinant of U and the determinant of A. All right, so this is what we can say. The determinant of A is equal to, and we have two cases here, okay, is -1 to the power of R multiply by products, a product of pivots in U. Okay, so this might be a little confusing. So let's say, let me give you a few more pieces of information. All right, so R, let's start with R. R is the number of times we perform row interchange. Okay, so R is the number of row interchange done within this process. And I forgot to say one thing. Let's put a note on the side. U, this matrix capital U, is in echelon form. Is in echelon form, meaning it's going to have some sort of pivot items, right? It's going to have some sort of pivot columns, right? So if it's triangular, then we know that the determinant is just the product of the diagonal, right? Let me say that again. If we know capital U is triangular, meaning I have all of the non entries on the diagonal, everything below that is 0. Okay. If it's triangular, then the determinant of U is basically the product of all the entries on the diagonal. All right, so here we can say that determinant of A is basically the product of the pivots in U, which are our diagonal. Now, here we are assuming if A is invertible. Okay, so this brings us to a one condition that we need to have is on the diagonal of U, we cannot have any zero. Okay? If you need some time to think about this, you can pause it for a second. So if we have a zero on the diagonal of U, then the determinant will be zero, which is our second case. Right? Determinant of A will be zero when A is not invertible. Okay. All right. So let's roll back and look at this part again. Okay. So we start with some matrix A, which is n by n. And we want to reduce it to this matrix U, which should be in echelon form, by doing only two types of elementary row operation, the row replacement and the row interchange. Now, the reason why we only want to do these two is because we don't want too much change in the determinant. Right? As you can see, row replacement does not change the determinant, and row interchange only changes the sign of the determinant. Okay? And then we also have to keep track of how many times we did row interchange so we can determine the sign of the determinant at the end. Okay? All right, so U will look like this, some sort of, it will look sort of triangular, right? Because it's n by n, and then we are in echelon form. All right, so there are two cases. First case is if you don't have any zeros on the diagonal of U, right? If you don't have any zeros here, then the determinant of A will be the determinant of U. Going back, we need to take care of the negative sign. That's why we have the -1 to the R, right? We did R many times of row interchange. That means the sign is going to oscillate between positive and negative R many times, right? And multiply by the products of the pivot of U, which gives us the determinant of this triangular matrix. Now, we can only do this when A is invertible, because if A is invertible, then we wouldn't get a zero on the diagonal. Now, if A is not invertible, that means we will have at least 1 0 on the diagonal of U. Then that will give us a determinant of 0, and there's not much we can do from there. All right, so all this is just to prepare us for the next upcoming topic. Okay, so let's look at the first theorem from 5.2. It's the invertible matrix theorem continued. Now, these 2 points that are given, they are actually very useful, and we actually used, I think, one of them in 5.1. So let's take a look at this. I'm going to write down some of it. So A is invertible if and only if, right, these two things, the number 0 is not an eigenvalue of A, right? Number 0 is not an eigenvalue. Okay, so let's talk about this for a little bit. If you remember, if we make a matrix triangular, then all the entries on the diagonal will be its eigenvalue. Right? Now, if you have an eigenvalue of 0, that means your matrix will look like this: A, B, C, and then somewhere here it's a 0, and then right, and then a bunch of zeros here. Okay. Right. So if you have a 0 on the diagonal of a triangular matrix, that means all the entries on the diagonal will be 0. All the entries on the diagonal will be your eigenvalue, right? Then here we say that there is a eigenvalue of 0. But if you find the determinant of this matrix, it's going to be 0, right? Because determinant of a triangular matrix is the product of the diagonal. And then you get a 0, which means it's going to be not invertible, right? So here we are saying if A is invertible, then the number 0 cannot appear on the diagonal of the triangular matrix, which means the number 0 cannot be an eigenvalue. Okay, let's look at the second one, or 20, right? Determinant of A is not 0, right? Determinant of A is not 0. And I kind of briefly mentioned this, right? If you have 0 on the diagonal of the triangular, then their determinant is 0, right? So if A is invertible, these two things, 0 cannot appear on the diagonal. Okay? Now, if one of these things happen, then we can conclude that A is not invertible, right? If you find a 0 eigenvalue, or if you find the determinant of a matrix being 0, then you can conclude that the matrix A is not invertible. Okay? So let me write it down. Okay? If lambda is 0, if an eigenvalue is 0, or if you find that the determinant of A is 0, then A is not invertible, right? This is also true based on the invertible matrix theorem. All right, so let's just take some time and look over theorem 3 very quickly. Theorem 3 is pretty easy to understand, so I'm not gonna write anything down. All right, so let's say A and B are n by n matrices. First, A is invertible if and only if determinant of A is non-zero, right? So we kind of talked about this in the previous theorem. Number 2, determinant of the product A and B is the product of the determinant of A and the determinant of B. So we also talked about that. Number 3, determinant of the transpose of A is equal to the determinant of A. And we actually proved this at the end of 5.1. Okay. Number 4, if A is triangular, then the determinant of A is the product of the entries on the main diagonal of A. And then we also saw that in 5.1 as well. Number 5, a row replacement operation on A does not change the determinant. We know that. We saw that already. A row interchange changes the sign of determinant. And the row scaling also scales the determinant by the same factor, right? So number 5, we also talked about this, I think a few sections ago, when we talked about determinant and the elementary row operation. All right, so that's just theorem 3. I just want to show you guys real fast right here. All right, so moving on. We talked about this in 5.1, that if we want to find the eigenvalue, right, then we want to make sure that this matrix A minus lambda I is not invertible, right? And remember, the reason of not being invertible is because we don't want just a trivial solution to this matrix equation, right? If the only solution to make this true is having x being the 0 vector, then there's no help to us, right? So we want to make sure that this is not invertible so we can find some non-trivial solution to this. Therefore, we can find lambda. We can find our eigenvalue, okay? So for this not being invertible, it means that the determinant of A minus lambda I is going to be equal to 0. Okay. Now think about this. If A is n by n, right, then determinant A minus lambda I is also going to be an n by n matrix. And furthermore, we know that the determinant is going to be 0. Okay. And this equation is called the characteristic equation. And if you find what the determinant of this is, you actually will get a polynomial of degree n, right? And once we get this polynomial of degree n, we only have one variable, which is lambda. So we just need to solve for lambda to get the eigenvalues. Okay, so that's the basic idea. And later on, we'll take a look at a quick example. Actually, I think now would be a good time to look at example 1. Okay. So we want to find the characteristic polynomial and the eigenvalue of the matrix 5, -3, -4, and 3. Okay, so suppose this is our matrix A. All right. And next, we want to find what A minus lambda I is. All right, so keep in mind that A minus lambda I is just lambda multiplied by the identity matrix. So we have a 2 by 2, which is A, so our I is going to be 2 by 2 as well. So we have lambda 0, 0, lambda, like that, right? Okay, and then go ahead and subtract it. I have 5 minus lambda, -3, -4, and 3 minus lambda. Okay. Okay, so notice that on the diagonal, we have all the entries subtracting lambda, right? And next, let's look at the determinant of A minus lambda I. Okay, and let's move on to the next page. Okay, so this is what we have, right? We want to find the determinant of that, and then we can set it equal to 0 at the end. All right, so to find the determinant of 2 by 2, you multiply that way and subtracting that way, right? So we get 5 minus lambda times 3 minus lambda, subtracting 12. All right, so expand that. All right, this is what we have, and reorder them a little bit. Lambda squared minus 8 lambda minus 7. All right, so this thing is our characteristic polynomial, and we know that this is equal to 0. And next, we just need to solve this equation, this quadratic, right? And it's pretty easy. Oh, made a small mistake. That should be 15. And this should be positive 3. All right, so let's solve this. Doesn't look like this is factorable, so I'm just gonna use a quadratic formula. Right, so negative b plus or minus b squared minus 4ac, so that's 12 over 2a. Okay, and by using quadratic formula and then simplify, we get two values, right? So we can say that lambda 1, first eigenvalue, is 4 plus radical 13, and lambda 2 is 4 minus radical 13. Okay, so we started by looking at the determinant of a minus lambda I. So basically, you just take the diagonal and then subtract lambda for each entry. And then go ahead and find the determinant, set it equal to 0, and that is your characteristic equation or characteristic polynomial right here. And then all you need to do is solve that, right? And depending on the size of your matrix, if it's 2 by 2, then you'll have a degree 2 polynomial. If it's 3 by 3, you get a degree 3. 4 by 4, you get a degree 4, and so on. Right? And basically, you're just solving some sort of polynomial, right? And we have a lot of methods to solve that. All right, next, let's look at the definition. Right? If A and B are n by n matrices, then A is similar to B if there is an invertible matrix P such that P inverse multiplied by A times multiplied by P is equal to B, or A is equal to P times B times P inverse. All right, so let's look at the first part first. All right, let's just want to talk about how we can go from here to here. All right, so let's say we know this to be true. All right, and what I'm going to do is I'm going to try to get rid of this P inverse and the P. Now, remember that matrix multiplication is not commutative. It means if you multiply a matrix on both sides, you need to make sure that are we multiplying in the front or are we multiplying at the back, right? Left or right multiplication, right? So what I'm going to do here is I'm going to do a left multiplication by P on both sides, right? So same thing here. And then I'm going to do a right multiplication of P inverse right here. So on the right. So I need to do both on the right. Okay, and what you'll see is that P multiplied by P inverse gives you identity. Same thing here, gives you identity. So you have on the left hand side, you have identity multiplied by A multiplied by identity, which is just A. And then the right hand side, you have P times B times P inverse. And that's this thing right here. Okay. So if A is similar to B, right, these two things are true, right? Or I should say these two things defines the similarity between A and B. All right, and moving on now, let's look at theorem 4. If n by n matrices A, B are similar, then they have the same characteristic polynomial and hence the same eigenvalues, right? So that's a nice theorem to have. And again, I'm not going to spend too much time on the proof here, but if you're interested, you can look at that over. All right, and moving on to our first remark, right? One, the matrices 2, 1, 0, 2, and 2, 0, 0, 2. Now, even though they have the same eigenvalues, right, it doesn't mean that they are similar. Okay, so keep that in mind. Right, if they are similar, then they definitely will have the same eigenvalue, but it doesn't work the other way around. Okay. All right, and second remark, similarity is not the same as row equivalence. If A is row equivalent to B, then B is equal to EA for some invertible matrix E. Row operation on a matrix usually change its similarity, right? So similarity and row equivalent, they are very different, right? So by performing elementary row operation, it can actually change its similarity, right? So those two are not closely connected together. All right, so let's take a look at example 2. All right, so we did example 1 earlier. Let's look at example 2, trying to find the eigenvalues. So first, we need to come up with our characteristic equation. Right, we want to find A minus lambda I. Right, and here I'm gonna show you a really fast way to do this. So you know that all the diagonal are going to be subtracting lambda. Right, so we just do 5 minus lambda, negative 2, 3, 0, 1 minus lambda, 0, 6, 7, negative 2 minus lambda. Right? So just add the minus lambda on the diagonal and then find the determinant and we're good to go. All right, so I'm going to find the determinant of this 3 by 3 by using the method that I showed you guys earlier. Right, like that. And then you multiply downwards and then subtract upwards. Right, so 1, 2, 3. And when you multiply downwards, they are all positive, right? Now you'll see that these two are actually going to be 0, so we don't have to worry about them, right? So first I have 5 minus lambda, 1 minus lambda, negative 2 minus lambda. And then plus 0 plus 0. I'm going to omit that. All right, next, going from bottom up, 1, 2, and 3. Right? And notice that they have to be subtracted. And then the last two are also 0, right? So we don't have to worry about that. This is the only one we need to worry about, minus 18 times 1 minus lambda. Okay. All right, and then that's our polynomial. Go ahead and expand those. All right, and then you will have something like this, a third degree polynomial, because we're looking at a 3 by 3. And next, let's try to solve this. All right, so here we go. Let's get rid of this negative sign first. Right? Minus 25 lambda plus 28. All right, so here we can do a little bit of algebra. Right? So you can use remainders theorem to check if that is a solution. Right? So let's see. I'm gonna check 1 and 1 negative 4. 5. All right, so 1, 1, -3, -3, -28, -28. Boom. Oh, there you go. Got it. All right. So one of the lambda is 1. So that means I can rewrite this polynomial as lambda minus 1 times lambda squared minus 3 lambda minus 28 is equal to 0. No, I'm pretty sure you guys have many different methods of solving this, but this is one of my ways. All right, and then we just need to factor that. So lambda minus 1. Oops. And what is that? 4 and 7. All right. Lambda minus 7. Lambda plus 4. Okay, all right. So here we have lambda 1 is 1. Lambda 2 is 7. And lambda 3 is -4. Right? And that's it. Right? So finding eigenvalues given a matrix, right? Find the determinant of A minus lambda I, solve the characteristic polynomial, and then you're done. Now, example 3, if you notice, that's actually a triangular matrix, right? A lower triangular matrix. If it's a triangular matrix, that means the eigenvalues are just the diagonal entries, right? But still, I want you guys to give that a try. See what happens when you try to find the determinant of the 4x4 matrix in example 3. So I'm going to stop lecture of 5.2 here. Stop at example 3. So everything below example 3, those are some extra materials that we don't cover in 5.2, but it's optional. But I decided, given the time being, we're not going to spend too much time on this. All right. So then make sure you check out 5.1, 5.2, and 5.3.